Good morning, everyone. It's a pleasure to share with you our recent work. It's unfortunate that I can't attend in person because of visa issues, so my colleague will help me to play this record. My name is Bohan Yu. I'm an undergraduate from Tsinghua University. This is my work done this summer during my internship at Rose Spatial Temporal Learning Lab at University of California, San Diego, where I was fortunate to work with Dr. Yadi Cao, Professor Duncan Watson Paris, Professor Liam Bergen, Professor Taylor Kirkpatrick, and Professor Rose Yu. The title of our project is Adapting While Learning, Grounding LLMs for Scientific Problems with Intelligent Tool Usage Adaptation. Let's first talk about the background. As we already know, large language models such as GPT or Llama series have shown remarkable potential in scientific domains, from answering textbook problems to contributing to research. However, there's a critical gap between their performance on simplified problems versus real-world complex scenarios. Consider the simple physics problems about a falling ball from the MMLU benchmark. Large language models can handle this kind of problems very well because they are highly simplified. But this kind of simplified problems don't reflect the complexity of real-world science. Let's look at the second problem about climate prediction. This represents the kind of complex scientific questions we actually need to answer. It asks about temperature changes in a city under specific emission scenarios. When faced with such problem, large language models are often falter. They generate answers that sound convincing but are factually incorrect. In conclusion, large language models demonstrate promising capabilities in solving simple scientific problems but often produce hallucinations for complex ones. So, how existing methods address this? Existing works focus on two distinct approaches to address this challenge. The first approach involves fine-tuning LLMs using a combination of human annotation and stronger model supervision, as illustrated in this workflow diagram, which is extracted from a work called SAIGLM. However, this method has a significant limitation, is that it demands extensive human annotation effort and relies heavily on stronger models for supervision. The second approach takes a different direction by integrating large language models with external specialized tools. For example, in the paper Mind's Eye, they augmented large language model with physics simulator module. When large language model receives a problem, it resorts to the simulator and gets the simulation result, and finally provides the answer based on the simulation result. Given the distinct characteristics of both approaches, let's analyze their respective strengths and limitations. Firstly, the fine-tuning approach. It has significant limitations. First, it demands massive amounts of training data from both human annotation and stronger models, which are both highly cost. There's also a fundamental issue, is that for complex problems that even state-of-the-art models can't solve, the knowledge distillation approach becomes futile. Most crucially, even after intensive fine-tuning, these models remain prone to hallucinations because they still have nothing to do for the complex problems. The fine-tuning method also have advantages. The fine-tuned models offer efficient inference and perform remarkably well on simpler problems, while maintaining their ability to generalize across different scenarios. The second approach, employing large language models as tool-using agents, presents different challenges. A major concern is the model's tendency to over-rely on provided tools. As we saw in the Mind's Eye example last page, the model resorts to using simulation tools even for the most basic problems that they can solve without tool using. In scientific domains like climate, tool usage is both time-consuming and expensive. This unnecessary tool dependency creates significant but unnecessary costs. Moreover, models don't actually learn from their tool usage. Then, when tools are not available, they lose their problem-solving capabilities entirely. Nevertheless, The LLM as agent approach does bring crucial benefits. It provides highly reliable solutions through validated tools and effectively handles complex problems. So can we combine the advantages of both approaches while avoiding their respective drawbacks? That is, can we maintain the efficient inference and basic reasoning capabilities of fine-tuned models while incorporating the reliability and complex problem-solving abilities of two augmented systems? Based on it, we propose our method that is called adapting while learning. Our approach consists of two key phases. The first phase is called world knowledge distillation, which is shown in panel A, which is the learning part. For all questions, the large language model interacts with tools to generate reliable solutions, which are then used for its own training through supervised fine-tuning. For open-ended questions, we also introduce a preference optimization mechanism. The model first samples multiple potential answers, then use tools to rank and sort these answers. Then we will use DPO to train the model with the generated preference pairs. The second phase, tool usage adaptation, is illustrated in panel B. It's the adapting part of our method. Firstly, we evaluate our model on a question set and split the question set into two parts. The first part contains the problems that the models can solve directly without tools correctly, while the other part contains the difficult problems that the models can't solve without tools correctly. We then train the model to follow the tool using traits for the hard problems and answer directly for the easy problems. The impact of our approach is visualized in panel C. After world knowledge distillation, the model begins to internalize knowledge, shown by the shifting vertical boundary. After tool usage adaptation, the model gets more intelligent tool usage decision, represented by the horizontal boundary adjustments. Let's go deeper into our method. First, the world knowledge distillation part. First, the large language model generates a solution by interacting with the tools. As you can see in the example, the X denotes the question and the I denotes the information gathered from the tool using traits. The model asks for the longitude and latitude of the place and use the latitude and longitude of the place along with other parameters to make some simulations and get the final result. Finally, it will use the gathered information to generate a solution that is Y. We then use this tool-generated solution Y to ground the LLM through our world knowledge distillation objective. This function essentially trains the model to maximize the possibility of generating correct solutions without data generated from interacting with tools. Thus, ground LLM with the world knowledge that was originally embedded in the tools, but now we want the LLM to learn themselves, to internalize the world knowledge into themselves. For open-ended questions, we also use tools to rank different answers and train a large language model with DPO, like shown in this figure. In the panel B, we can see that the question is to design a new maritime route between two cities to maximize the temperature increase. And the large language model proposed three different proposals, and the tools or emulators is used to simulate different proposal, and it finds that the temperature of the first proposal is 6.3424, and the temperature for the second proposal is 6.3449. And when it simulates the last proposal, it finds that it's invalid because the question asks for a maritime route, but it finds the route it proposed, it interacts with the land, so it gets the rank. It's Y1 is better than Y2, and Y2 is better than Y3, and we got the preference pair, and we can do some preference optimization based on this kind of data. Then we come to the tool usage adaptation part. First, we evaluate the model's performance on a dataset and partition the questions into two subsets, D easy and D hard. This is shown in the diagram where Q1 leads to an incorrect answer and becomes part of D hard, while Q2 leads to a correct answer and becomes part of D easy. We then set different alignment targets for these two subsets. For D-easy, we use J-easy to train the model to maintain its direct answering capability for easy questions. For D-hard, we use J-hard to train the model to follow two using traces for more challenging problems. We combine these objectives into a unified training objective to ensure the model learns both when to use tools and when to answer directly. Then we want to build a adapting while learning paradigm. A direct thought may be to do them iteratively or do them step by step, but as is shown by previous work and our preliminary experimental result, it shows that knowledge acquired under one scenario does not readily transfer to another. It means that training exclusively in one scenario can degrade performance in the other. And the scenarios here means whether it have available tools, whether it is a tool using scenario or it is a direct answer without available tools scenario. For example, when a model is trained solely on knowledge-based data without tool interaction, it may lose its function calling abilities needed for tool use. Similarly, training only with tool-based solutions may weaken the model's direct reasoning abilities. Therefore, we propose a mixed loss that simultaneously considers both word knowledge distillation and tool usage adaptation objectives. This balanced objectives ensures the model maintains both capabilities. The effective of our mixed training method is shown in the experimental result as shown in the as shown in this figure. In our ablation study, if we ablate the word knowledge distillation or tool usage adaptation, the model will both over rely on tools, and if we eliminate the word knowledge distillation, it won't learn more knowledge. Only with our mixed method we can get a result that shows the model not only learns knowledge but also gets a more intelligent tool usage adaptation. As you can see, the blue part is the easy problem and the dark blue part is the easy problem without tool usage, which means to solve this problem the model don't choose to use tool. But you can see this blue part, the shallow blue part, it means that for easy problems the model also resort to tools. Our experiment includes 6 datasets, 2 public datasets, mass, some bench, and 4 our custom created datasets, which are respectively logical for soft and rigid body problems, partial differential equation problem, climate science problem, and epidemiology problem. Our custom datasets capture real-world complexity and dynamics in the areas of critical importance to human welfare. Our custom datasets were carefully constructed through a systematic pipeline. We first developed domain-specific question templates through expert consultation and based on tool functionality. Then we generate individual questions and their answers by sampling parameters within scientifically valid ranges. Most of our custom datasets consist of multiple choice questions, while the climate science dataset being an exception that it also includes open-ended questions, such as proposing climate change mitigation policies. We report the answer accuracy comparison across all datasets in the table above. It shows the effectiveness of the word knowledge distillation in our method. As we can see, our method substantially outperforms all baselines on our custom created datasets that were not commonly covered in pre-training. While our model does not surpass current state-of-the-art models on public dataset, it shows significant improvement over the base model without fine-tuning. This performance gap on public dataset is likely due to the larger parameter count and specific optimization of state-of-the-art models on the open source datasets. We also evaluate our methods along with baselines on open-ended questions. We show our result with win rate because for open-ended questions, there's not a definite correct or wrong. In the win rate figure, we can see that the RL model further surpasses the SFT model, which shows the effectiveness of the preference optimization method. We also show our method's resistance to noisy data. As we all know, generating solutions via large language models or human expert annotation. They both inevitably introduce noises, but whether these noises largely influence the model is a crucial problem. As we can see, in the SFT method, if the model is fine-tuned with data with increasing noise, the performance of the model degrades a lot. But with our method, it don't degrade a lot, except that the data is 100% noised. It's because that when the model finds that it can't answer the problems correctly, it will resort to tools. It shows the adaptive ability of our models. Then we report the tool usage accuracy to show the effectiveness of the tool usage adaptation part of our method. We present the tool usage adaptation in this table. Overall, our trained model achieves the best tool usage accuracy across all datasets, except for SunBench where it ranks second, demonstrating the ability to make intelligent decisions on tool usage. In contrast, other models exhibit accuracy around 50%, which means that it's either overconfidence or over rely on tools that will make these two terms, one to be 0 and one to be 100, and half of their sum is 50. Besides the advantage shown in the table, we further investigate the tool usage decisions on the mass datasets, which have their questions ranked in different difficulty levels. Our trained models exhibits a reasonable increase in tool usage with growing question difficulty, while the base model shows an over-reliance on tools regardless of difficulty. And Cloud 3.5 demonstrate overconfidence in different kinds of problems regardless of problem difficulty. It's near to our conclusion. Firstly, we introduce a novel two-component training paradigm that enables LLM to adaptively solve real-world scientific problems of varying complexity. As we have introduced, it should directly answer the easy problems and resort to tools for harder problems. Secondly, we construct 4 additional datasets spanning various scientific domains, including both questions and solutions, to facilitate future research in this direction. Thirdly, experiments on both custom and public datasets demonstrate the effectiveness of our work, resulting in better answer accuracy and more intelligent tool use. That's all. I hope that you would love our work. And our work is already public on arXiv, and you can take a picture of our slide. And if you are interested in our work, you can later search for it. And my name is Johan. If you have further questions, you can ask me through my email, and you can also visit my personal page to get my connection information. My colleague Vijay Makli will help me to host the QA session. If he can help with you, you can email me and ask your question. Thank you all. I hope you enjoy our work.